Sometimes, child's play could give us a lot of insight into physics as well. For example, look at these blocks. If they are stacked one on top of the other in this manner, they are stable till a point. But beyond a point, they tip over. See? Why does this happen? What is it that makes the blocks tip over? We'll discover the answer to this and much more in this episode. Hello and welcome to the show on equilibrium of rigid bodies. Suppose I stand here without moving. Am I a body in a state of equilibrium? You are right, of course. I am in a state of equilibrium, the topic central to today's show. In this episode, we'll learn about when is an extended rigid body in equilibrium, what are the conditions for equilibrium, definition and location of center of gravity of rigid bodies, and of course, the segment all of you look forward to, the exam decoded segment. All around us, there are examples of how critical equilibrium is. From a tall building to the imposing Qutub Minar, to the humblest shed, they must all be designed in a way that they won't topple over. A suspension bridge shouldn't collapse. A ladder leaning against a wall should hold up, as should a crane hoisting a bucket full of concrete. Let's study and analyze how the systems under the action of various forces achieve equilibrium. If we model a body as a point particle, it is in equilibrium whenever the net force, which is the vector sum of all forces acting on it, is zero. But in the case of an extended body, where forces act at more than one point, this condition of net force equal to zero is not enough for determining whether the body is in equilibrium. The condition for equilibrium needs to be modified for an extended body to imply that there is no linear or angular acceleration of the body in equilibrium. The sum of the torques about any point should be zero for rotational equilibrium. If no net external force acts on a body, the object is either at rest or its center of mass is moving at a constant velocity. For example, when you are on a weighing machine, there is zero net force acting on your body. And such a system, which is under zero net force, is said to be in translational equilibrium. The second condition for an extended body in equilibrium is that it should have zero angular acceleration. That is, for a rigid body to not have any tendency to start rotating about any point, the necessary condition is that the sum of external torques must be zero about any point. As you can see, the forces acting on a perfectly balanced weighing balance or a balanced seesaw are such that the net torque due to various forces are zero about any point. Have you seen a flamingo recently? Chances are you've seen them stand with one foot tucked up against the body. Flamingos have a broad webbed feet. How does this enhance the bird's stability when standing on one leg? To remain in equilibrium, a standing flamingo must keep its center of gravity, the point where flamingo's weight can be considered to act for the purposes of calculating torque over the foot that touches the ground. Before we understand the logic behind this trick, let us define and understand the center of gravity of a rigid body. In most equilibrium problems, one of the forces acting on the body is its weight due to Earth's gravitational pull. The weight doesn't act at a single point in the case of an extended rigid body. But for the purposes of calculating the torque due to the weight, we can assume that the entire weight acts at a single point called the center of gravity of the object. So the center of gravity of a body is that point where the total gravitational torque on the body is zero. Now, if the body is fixed to rotate at the center of gravity, then the torque due to the weight about the center of gravity will be 0. A table at rest will experience 0 torque due to its weight about point G, which is its center of gravity. Okay, now that you know what the center of gravity of a rigid body is, how do we locate it? For symmetrical objects, we use symmetry considerations to locate the center of gravity of a rigid body, just as we do for center of mass. For example, center of gravity of a homogeneous sphere, cube, circular sheet will be at its geometrical center. It's time to put on your thinking caps now. Let me ask you a question here. In the figure, there are two people lifting a heavy log. Which of the two people is supporting a greater weight? The person on the left, the person on the right, or they are supporting the same weight? For more such questions, don't forget to visit our website, topperlearning.com. Now you think about the answer while I take a short break. Stay tuned. Welcome back. Before the break, my question to you was, in this figure, there are two people lifting a heavy log. Which of the two people is supporting a greater weight? The person on the left, the person on the right, or they are supporting the same weight? And the answer is, the person on the left is supporting a greater weight. Let me explain this. The momentum of the left person is less, and therefore he has to apply a greater force on the log to keep it in equilibrium. The net torque about any point due to the upward force applied by the two people and the weight of the log should be 0. If person 1 is applying force F1 at a distance x1 from the center of gravity, and person 2 is applying force F2 at a distance x2 from the center of gravity, and we choose the center of gravity to calculate the torque, the weight won't produce a torque about the center of gravity, because the lever arm for the weight is 0 about the center of gravity. So what we have is F1 times x1 is equal to F2 times x2. So if x2 is greater than x1, then F2 is less than F1. So it is the person on the left who is supporting a greater weight. This brings us to an important concept, the significance of center of gravity. Let me answer this with a scenario. If a body under the effect of gravity is supported or balanced at a single point, the center of gravity is always at or directly above or below the point of suspension. Now, if this does not happen, the weight will have a torque with respect to the point of suspension, which means that the body will not be in rotational equilibrium. Following a similar reasoning, a body supported at several points must have its center of gravity somewhere within the area bounded by the supports. This explains why a car can drive on slanted road, but if the slant angle is too great, it'll tip over. Don't forget to visit our website, topperlearning.com, for more revisions and practice. And remember, it's your universe. Know the rules.